Let's talk about equilibrium here. You'll have heard this in level 1. Equilibrium was when we had no net force. So, and from Newton's second law, no net force just means no acceleration. It doesn't mean you don't have a velocity. So something could be going very fast and still have no net force, or it could be stationary. So a few of the examples we used, I think in level 1, we would have a car, we would say it's got a thrust, we would say it's got a drag, we would say it's got a support force, and we would say it's got a weight force. And if those vectors, these are all vectors, so I call it Fs, Fw, Ft, Fd, drag. If those vectors are all equal, then there's no net force, the forces are in equilibrium, and therefore there is no acceleration. Of course, no acceleration. It happens when someone gets to terminal velocity, right? You're falling down in this parachute. Actually, better make those solid, otherwise he's going to have a problem, isn't he? Now, at a certain point, so mg stays the same the whole time, but at a certain point, the drag on that parachute exerts an equal and opposite force. He is now in equilibrium, and he now has terminal velocity. All right. So equilibrium, you may have seen those examples, but what I wanted to show you was another one where we make it a little bit trickier, eh? Let's try and keep that a little straighter. This time we've got an object. Try and keep these about the same angle, whatever it is. And we've got a mass like that. So that might be 25 kgs, right? Now 25 kgs exerts a force of a weight force of 25 times 9.8. 25 times 9.8, and we've got 245 newtons. Now, according to F equals ma, if you've got a force, you should have an acceleration, but we all can see that an object like that's just going to sit there, right? So no acceleration. Let's say this angle is 45 degrees, that's 45 degrees, right? Now, the only way this object is not going to be accelerating down is if it's got an equal and opposite force up, right? Now, the only way it can do that is through the tension in these cords. But the tension in these cords can only exert a force in that direction, right? Force in these cables can only exert in that direction. So what we need, and there's two of them, so each one needs to have a vertical component here. See, we can split these vectors, this tension, into, again, horizontal and vertical components. Each of those horizontal and vertical components, each of those vertical components is up and across on this one to the right, up and across to the left on this one. That's the tension in the rope or chain or whatever it is. And we know that we need a vertical force up of 245. That means each one needs to be 122.5, right? So if each vertical force needs to be 122.5, then F, the force of tension, or Ft, we can calculate it. So if this angle is 45 between the horizontal and this one here, all right, then we know that the angle here is also 45 degrees, this one. Everything's 45 degrees. So we know that Ft times 45 degrees must equal 122.5. So Ft times the cos of 45 degrees must equal, sine of 45 degrees must equal 122.5. I know that those of you that are good at maths are going, haha, it doesn't matter. Sine and cos of 45 are the same thing, right? But we can now do this. All we need to do is to divide 122.5 by the sine of 45, and we'll have Ft. So we'll do that, 122.5 divided by the sine of 45, and we've got 173.24. That'll be newtons. That's Ft. All right. Now you may be asking, or you may not, that what about these horizontal forces? We've got the Ft, we've got vertical forces up of 122.5 on this one, 122.5, that cancels out the 245, but we've also got 173.24 on this one, and 173.24 this way. You can see they also cancel out. So this whole object with these forces cancels out because the vertical forces are equal and opposite, and the horizontal forces are equal and opposite. This object is in equilibrium. It is not accelerating, it is stationary.